I will also do it just in case there is a problem. Yeah. Okay, so astrophysical relevance of polytropic stars. And then I will come to one important thing, which is about convective transport of heat in stars. So in stars, the engine which produces heat is right at the center. And we see that that heat, energy comes out with the stars. So the question is, how does it get transported from center to the surface? We know that there are three ways in which it gets transported in general. One is convective, conductive, and radiative. Now, the conductive one is usually the relevant one in solids. But stars are not solids. They are all fluid spheres. So the two main mechanism of heat transport in stars is convective and radiative. What happens is, when there is a heat generation in the center, it tries to radiate it out. But then it is not vacuum. There is ionized material, so the radiation cannot freely pass through the material, and so it exerts a pressure. Now, if the radiation rate is very, very strong, then, if the energy generation rate is very, very strong, then the radiative process is not sufficient to carry the radiation. And so the radiation gets, the amount of radiation in the center keeps increasing till a whole blob which gets heated, and the entire blob, the matter starts flowing out, which is convection. And so today we will talk about convective transport, and the radiative transport is a very detailed process, and we will come to it in very great detail on radiative processes. So after this, we'll just talk about first convective transport, and then I will talk about role of radiation pressure in stellar equilibrium. So basically what happens is, till now we have been talking about stellar equilibrium by saying that the thermal pressure of matter compensates for the gravitational force. But now I can have a star in which there is so much of matter, because you see, the thermal pressure is proportional to temperature, whereas the radiation pressure, from Stefan Boltzmann law, is proportional to T to the power 4. So when the temperature is more and more, at one point, the radiation pressure becomes so enormous compared to thermal pressure that it dominates over thermal pressure. And the star is primarily balanced by radiative pressure. We will talk about this and get the equation of state for mixture of radiation and matter. And then I will give a brief semi-qualitative and semi-quantitative brief discussion. Okay. Brief semi-quantitative description of stellar evolution of stars. The reason we are taking now is that now we would have built sufficient ground to actually discuss how stars evolve, at least in a semi-quantitative way. And then I will come to this important and very elaborate portion of radiative processes and transport in stellar interior. For next few classes, this is going to be the plan. Okay. So let us now, so what I will do is, I will first briefly recapitulate something which I did towards the end. Namely, if I have a polytropic star, then why is it? I mean, I had mentioned about if I add a certain mass, then there is a metastable equilibrium. And, before it settles down to a new equilibrium, a stellar equilibrium. I will just briefly recapitulate that. And then I will go over to another astrophysical application in which if you have a binary star, two stars going around each other, and one of the star is rotating, and mass is transferred from one star to another, then under what condition the other star's spin increases, under what condition it decreases. Okay, this is very important, especially in the context of things like AstroSat and all those Indian satellites and many other satellites which have been being launched for studying, say, X-ray binaries and so on, X-ray binary stars and so on. So I will tell the basic physics of spin up, spin down for this. Okay, so now is that fine? I mean, any questions?
It's fine, sir.
Okay, fine. So now let me go back to, let me start with what I had left last time. That is polytropic systems and evolution of stellar radius on mass transfer. Okay. So fine. So now recall two expressions which we had got for mass and for radius, which was mass is equal to n plus 1 by 4 pi g and then 3 by 2. I mean, this is just, you have referred to the previous. Have you sent you the notes of last time of Astro?
I
Hello?
don't think so. I don't think so.
Yeah,
I will do it. I will both of you give both of them today. So this is 4 pi, but you have the recording, right? I mean, at least who recorded.
Yeah.
I will share the recording also.
Okay.
This is Xi1n. That is for the n, for the polytropic index n, the size of the star, radius of the star in terms of the dimensionless quantity Xi. Okay. Xi1n and then minus theta prime 1n, which is d theta by d Xi, the derivative of d theta by d Xi, which is prime. So of the nth polytrop at the point where the surface of the star is there. You understand this, right? This terminology.
Yes, sir.
Okay. So this is just a numerical factor. And then comes the important thing, which is k to the power 3 by 2, central density 3 by 2n minus half. Just to recall, I have P is equal to K rho power 1 by 1 plus 1 by n. This is how K is defined. Similarly, radius is defined as alpha times Xi1. And if you put in the values of alpha, I get n plus 1 by 4 pi g to the power half into Xi1 n multiplied by k power half rho c to the power 1 by 2n minus half. And with these two together, we had derived that k is equal to g m to the power n minus 1 by n r to the power 3 minus n by n into a numerical factor which was n, which is basically involves xi1 and theta prime 1. Okay, so this was the k, and if k is a constant, okay.
Yes, it should be xi1 n square, right, in mass.
Aha. I think I'm missing a term there. That should be cube, is it? Just a minute. I'll just get it. Yeah, maybe I'm just missing that.
No, it's a square, I guess.
This is a square, is it? Wait. No. There's something more complicated than that. No. Wait. I will find this out. Mass will be where is mass? Oh, I need to. Oh, okay. Just a minute. Oh, yeah. You are absolutely right. You mean here it has to be square, right? Is
Yeah,
that what you're saying?
yes.
Okay, fine. Okay, yeah. And so you have this, and then k is equal to this. And if k is a constant, okay, if k is constant, and that is where the trouble lies. If k is a constant, then I have mass proportional to r to the power 3 minus n by n minus 1. Okay, so this, and that's what I was telling, that no different situations of different values of n and the conditions where the mass with increase in mass radius decreases. So I had just done all this. But now there is a catch here. And what is the catch? And in order to understand that, let us just look at first the other physical parameters. I have rho c, no, Pc is equal to k rho c to the power 1 plus 1 by n, which is what we started out. But if we assume that the material inside is an ideal gas, then I also know that Pc is equal to rho c into kT, that is Boltzmann constant, divided by the mean molecular weight at the center multiplied by MP, mass of proton. And with these two together, one got that the central temperature is equal to K mu C MP by Boltzmann constant into rho c to the power 1 by n Okay. Fine. Now, in reality, in practice, okay, so here, so we find if K is constant, then Tc is proportional to rho c to the power 1 by n. It means that if you have a higher central density, higher the temperature, which sounds fine, but there's a catch here. The system, when being balanced by thermal pressure, between thermal pressure and gravity, what is the source of thermal pressure? Source of thermal pressure is nuclear fusion at the center. Now, the nuclear fusion at the center, its temperature is independently governed by the fusion temperature. So it is independently governed by the fusion temperature. Okay. And that has nothing to do with what is the rho C and so on. So in practice, Tc is fixed, which is of the order of, I think, 10 to the power 7 Kelvin or something. Which means that this capital K, which is there, it cannot actually be a constant. It has to be a thing which is temperature dependent. So, not temperature, density dependent. So this implies that actually K is proportional to rho C to the power minus 1 by N. Okay. Are you with me?
Yes, yes.
Okay. Now what I do is, I now use these. These and say now that mass is proportional to K power 3 by 2 rho C to the power 3 by 2n minus half, which is proportional to rho to the power rho to the power minus half. Minus half, right? Yeah. No. Something wrong, something wrong, something wrong.
1 by n minus half.
Wait a minute, just some mistake.
2.
This is K is minus 1 by 2. Oh, what is this? I should get mass proportional to rho C to the power minus 1 by N. No, sorry, it is minus 1 by, yes. No, K is proportional to this one. That is all right, yeah. So mass is proportional to rho C to the power minus half. And similarly, I have R proportional to K power half rho C to the power 1 by 2n minus half. And this is also proportional to rho C to the power minus 1 by half. And these imply, very interestingly, that mass is proportional to radius. Okay, it means in real stars, which one calls, which I'll come to while stellar evolution I'm doing, as main sequence, mass scales as radius. Okay, so now you have two things. Now you have this competition. If system is pure polytrope, which means K equal to constant, we have M proportional to, here we had, right? M proportional to R power 3 minus N divided by N minus 1. If system is a main sequence star, then we have the central temperature is constant and not K is a constant. And then we have mass proportional to radius. Is it okay so far?
Yes, sir.
Yes.
And now let us see, this is what I was telling you last time in brief, so I'm just elaborating it. Let us see how a system evolves under perturbation. So suppose I have, as I had drawn last time, in which I think Harish pointed out that this is just basically the metastable thing. So I have two lines So I have plotted it as log of, say, mass by solar mass, just for making dimensionless, and log of radius by solar radius. And now, since it is a log-log graph, power law will be a straight line. So let us say that this is a straight line, which is governed by this thing. And there is the another one, which is mass proportional to radius, which is the main sequence. And suppose a star is with this mass and this radius to begin with. And now what I have done is, okay, now I perturb it. By adding sums. Okay, so let us see how it evolves. Okay, what happens is, the moment you do that, from this point, mass increases to, say, this level. This is m plus delta m. And it may sit, I mean, if suppose the radius doesn't change mass, it will sit right here initially. Okay. Now there are two time scales we need to calculate. First of all, initially what happens, the temperature changes. So on adding mass, first temperature changes to be on main sequence. It needs to radiate out the heat to maintain Tc so that it remains in main sequence. You understand this? Because in a main sequence star, in the usual star, the central temperature is fixed by fusion. It can't change to have equilibrium. Okay?
Yes.
Yes.
Okay. So it means that this is what is due. So we need to, so there is a time scale. Okay. So time scale to radiate out the heat. Extra heat. That is the next thing. And what is it, this one? So the energy inside the system, so this is called T thermal, which is equal to energy in the system divided by luminosity, which is energy emitted per unit time. So this roughly tells me the time scale over which it will radiate out the extra heat. And this is of the order of Gm by R. This is the potential energy. So from virial theorem, it will be same as the kinetic energy and hence the energy of the system. Energy is one divided by the luminosity. Sorry, this is, no, this is m square here. And say for sun, for example, this is of the order of 3 into 10 to the power 7 years. Okay, so this is one time scale. Then is the one which is the time scale to readjust and remain on the same polytrope. And that time scale is basically, okay, so we calculate this. So this is actually, okay, so this basically involves adjustment of pressure, density, okay, and the speed. You know that speed of signal, which is a sound signal, when there is pressure and density, is Cs, which is equal to square root of dP by d rho. This is the speed of sound in a material. So it is a speed, since it's a pressure and density difference, any perturbation gets communicated by speed of sound. Is this okay? Hello?
Yes.
What about the others?
I'm not sure, but I could relate to it.
No, you see, the question is, if I suppose take a cylinder and at some place, I increase the pressure for some reason, this has to get communicated to make it homogeneous.
Yes.
So what is the speed at which it will communicate? It will be how pressure changes with density.
Yeah.
And the speed which governs this is acoustic speed, which is dP by d rho square root. So that is why any pressure difference always gets evened out at a speed which is at the speed of sound.
Yeah, but in that medium.
In that medium, yeah. In that medium. Okay, so speed of sound. And the length scale, the relevant length scale is the radius of the system, which means time scale of adjustment from dimensional analysis is of the order of R divided by CS, which is equal to the radius divided by dP by d rho square root. And for sun, this is of the order of 1 day, which is the same as dynamical time scale. Okay, and so this is equal to T dynamical equal to. Okay, and so you find that hence within a day, it adjusts to a new mass radius configuration with same n, but takes 3 into 10 to the power 7 years to attain a new equilibrium of a standard star. So relevance of, so although this polytropic index is not relevant to study main sequence, okay? So polytropic analysis not relevant in main sequence, but for about 10 to the power 7 years, it is in a metastable polytropic case before finally settling to main sequence. And it is this time when this whole analysis becomes valid. So what it means is, so it's actually about 10 million years when this analysis is valid. So it is not that we are doing it purely for an academic curiosity. Is this clear?
Yes.
Yes, sir. I
So
get
just the reason why we are doing all. So the point is, although this is not valid for a standard star, I was just giving a reason. Why is it that it is important that we study this? Okay.
Yeah, I have one doubt. Like, why did you call it the dynamic time scale and the other one as a different one? I understand.
That is because the dynamical time scale, because it depends on pressure, density, and the mechanical readjustment of the system to get a new equilibrium. Whereas the previous one was how far the heat is transmitted outside, so it is thermal.
Yeah, I get it. The other one, both the mass and the temperature remains constant, so it does not change the time. Is that what you said? For the main
The
sequence.
mass, of course, changes. I put extra mass.
Huh. No, after you put the extra mass.
Yes, so the temperature does not change.
So the
In order
luminosity
for
does not change.
temperature not change, the extra heat has to be given away. So there is a thermal process.
Okay.
So it is thermal time scale.
Okay.
Whereas
got
in
it.
the other one, there is a mechanical readjustment, and it needs to a mechanical readjustment for getting a new equilibrium. So it's dynamical.
Got it. Got it.
Okay, fine. Now I will talk about one more very interesting aspect of these polytropic things in the context of binary stars. Okay. Relevance of polytropic case for, I call it spinning stars, not necessarily binary, but that's what usually it was happens. Spinning stars. So typically this happens when you have two stars which are going around each other. So I have star 1, I have star 2. This is the common center of mass, and this star goes around the center of mass, and this star also goes around the center of mass. Okay. Now, what happens is in the non-inertial, that is rotating frame, the potential consists of gravitational potential of 1 plus gravitational potential of 2 plus the centrifugal potential due to non-inertial frame. It is in that central force motion, you have the L square by 2m r square. It is that thing. And if I go to that frame, so in the rotating frame, just give me 2 minutes. I'll come. Yeah. So in the rotating frame, the way it will look is the following. I have S1, I have S2. The potential energies, because of all these three, very close to S2, I will have almost spherical with slightly distorted because of rotation. Similarly over here, but when I am somewhere here, there will be a combined potential. So the equipotential surfaces will have a very interesting structure. The structure of equipotential surfaces will be, this is one. When I go further away, they will become sort of distorted. They will not remain spherical. And there will be one point where all the forces are balancing each other. And then the equipotential surface will be like this. And this equipotential surface is very important and very relevant of something which happened recently for the Indian astronomy, which is the Aditya mission and the Lagrange point. So I'll just mention a few things here. So what happens is, if I have in this non-inertial frame, I have one point, I have a second point. Now there is one, suppose this is the heavier object. So the equality of the potential in between will go further away than 2. This you understand, right? Because in order to make, if this is less and this is more, then for the point where the potentials are equal, it has to be closer to 1 and farther away from 2, so that the effect of 1 is more and the 2 is less, so that they equalize each other. Are you with me?
Yes.
Yeah.
Okay. And now, then there will be, so this is a bit exaggerated. So let me just keep it somewhere over here or something like that. And what is happening here? Here again, all these three forces are balancing, but they are not the only places where it balances. At one point here, there will be a gravitational force because of 1, the gravitational force because of 2, and the centrifugal force because of the rotation. And this will balance. Similarly, over here also, there will be a gravitational force in this direction, gravitational force in this direction, and centrifugal force in this direction. That will balance. Then there will be 2 points over here, which again will be gravitational force because of 1, gravitational force because of 2. And if this is the center of mass about which it is going, the centrifugal force here. And symmetrically, there will be a point here where the centrifugal force is here, gravitational force because of 2, and gravitational force because of 1. This point is called the L1 or the Lagrange point 1, where in the context of the Earth-Sun system, this is the point where the Aditya satellite has been placed. And the idea is that since here the derivative of the potential is 0, you require very minimal amount of energy to keep it co-rotating in the same frame. So it is like a stable equilibrium. And there are these other points, but this is important because we need a position where Aditya can see the sun and we can see Aditya and get the information. Is this clear?
Yes.
Is
This
this
will
the
be a
Rothschild
one
lobe
point.
that is inscribed in Ayukha?
Pardon?
Is this the Rothschild lobe that they built in Ayukha?
Yeah. So what happens is in this in this point where the potentials are equal, here the inside the potential is like this. Here the potential is like this. Very much outside the potential is like this, but at this point the is like a balloon. This is the Roche lobe. So if this star expands, this is the equipotential surface. So till this balloon fills up, nothing will fall here. Once this fills up, matter will start falling here into this star and it forms the accretion disk. And this is the thing where I will be talking now about what happens to this star one. Can I go ahead?
Yeah.
Others?
Yes. Yeah.
Okay. So let me move this and then put a simplified picture for what I require. Okay. So basically, so I have here star 1 and here I have star 2 and this is the Lagrange point and the matter is flowing from star 2 to star 1 because of the overflow of the Roche lobe or that balloon. So now what I'm saying is the following. Now, in general, S1 will be spinning. Say it's a spinning neutron star or something. And then matter is being poured in almost radially, not exactly radially, but almost radially. Suppose I just neglect the angular momentum carried by the matter. Then what is it that one can say? So now, the angular momentum of S1 is equal to, rather I will say proportional to, m r square times the angular velocity. Okay, this is the angular velocity. This thing. Okay. And now I can ask the following question. When mass is transferred and no angular momentum is added or removed, then what happens? Then delta J is equal to 0. Now, delta J is equal to 0 implies delta mr square omega plus mr square delta omega is equal to 0. And hence, delta omega by omega is equal to minus delta m r square by m r square. Is that all right?
Yes.
Fine. Now I know that once again, if S1 is a polytrop, I know that mass is proportional to r power 3 minus n by n minus 1. And so if I put these two together, I will get delta omega by omega proportional to minus delta m to the power 5 minus 3n by 3 minus n. And so, delta omega by omega is proportional to minus 5 minus 3n by 3 minus m times delta m. Okay? Am I right in this? It's a small mistake I'm doing, I think. No, let me just calculate
I
it.
think 1 plus n.
Yeah, something is there. Okay, just a minute. Let me just do that. Okay. So I have, let us just put it here. So I have m into r square is proportional to m into, you substitute r in terms of this, m to the power n minus 1 by 3 minus n, which is equal to m to the power 3 minus n plus n minus 1, which is wrong. How is this? What did I do? Oh, what am I doing? Sorry. Okay, so this. Okay, so this is equal to, so this gives me, let me write this. This implies R is proportional to m power n minus 1 by 3 minus n. Okay, and so R square is proportional to 2n minus 2 by 3 minus n, and mr square, this is m to the power, mr square is proportional to m 3 minus n plus 2n minus 2 divided by, I'm doing some, acha, okay, divided by this one, 3 minus n. Okay. And don't know, delta mr square, delta log of mr square. Okay. And so I have delta, yeah, delta mr square is proportional to, this will be what? This will be n plus 1. Am I right? Divided by 3 minus n. It's okay, no?
Yes.
Okay. And so delta mr square by mr square is proportional to, this is m to the power, is equal to m to the power n plus 1 by 3 minus n divided by this thing, which is
It's the same.
Wrong, I am wrong. I don't know what is what I mean.
I think delta m power n plus 1 by
I-
3.
Yeah. No, I'm goofing up. Okay. And so I have delta m r square is proportional to please calculate and see. I don't know. I am not getting it what I should be. See, I am putting it here and I'm calculating delta mr square and I've calculated delta mr. This is mr square over here. I suppose there is no problem here. 2n minus 2 divided by 3 minus n for r square. I multiply by m. So I have So I have 3 minus n and I have this. You know where is the mistake? I know. There is a mistake. There's a mistake. Just a minute. In the there is the mistake. This is 1 minus n. Just check your notes earlier. Right? Isn't it?
Yes.
Yeah, here. It's 3 minus n by n minus 1. And it's just 3 minus n by n minus 3. Oh, they are doing the mistake all throughout, is it? This was okay. 3 minus. No. Just a minute. Oops. Was this wrong then? I mean, p minus n by n minus 1. But what am I doing? Why am I getting this? Oh, this was a mistake throughout here. And then there is this correction. Oh, let's see. This is R. It was K. K is equal to.
Says it's not a mistake throughout. Like we have written it wrong only this time.
Is that so? Just a minute. N minus 1, 3 minus n.
I
Minus
think we have
n.
previously also written 3 minus n by n minus 1.
Yeah, there is some mistake I have done.
No, but previously, what do you mean? Like today's lecture or last lecture?
Yes. In today's lecture also we wrote 3 minus n by n minus 1.
But I think in the earlier lectures, like we wrote it right. N minus
Yeah. In
Yeah,
earlier
yeah,
3
lectures.
upon n minus 1.
Yeah.
So it goes on the other side. Oh, yes. Okay. So this is where the mistake is. So if I take this edge, there will be a minus sign. This is the mistake, right? 1 minus n. Is that okay?
I think screen sharing has stopped.
Yeah, we don't see the screen.
Oh, I see. Okay. No, don't worry. I was not doing any questionable activity. It just happened by itself. Can you see the screen? Just a minute. Yeah.
Yes.
Can you see the screen?
Yeah.
Okay. So this was the problem over here. Right. So because this is this one, so let me put it this way. If K is equal to constant, then I have M 1 minus N by N is proportional to R3 minus N by N. And that's what gives me. I forgot to put that thing, that minus sign. Is that all right?
Yes, yes.
Yes.
Yeah. Okay. So now if I make that correction, then these are all fine. And yeah, so I will have 1 minus N and then, yeah, which is fine, right? After that, there is nothing. Okay, then we just come here. Okay. So, my God, ये क्या हो गया? Again, it is wrong, is it? I don't know. M is 3 minus. Some goof up I am doing like mad. This is 3 minus N, 1 minus N, 1 minus N. Is this correct? Let me just unit. Yeah, this is all right. Huh. So, oh, this is where I goofed up. Yeah, it's 1 minus N. Okay. But then this is all right. Oh, yeah. Okay. This is very. Okay. Hello? Hello?
This is from Telecom Department regarding blocking all registered mobile phone number under your name after 2 hours. For more information, press 9.
Okay. So, it is. Are you people also getting this call suddenly saying that your mobile phone is going to get blocked after 2 hours or something? No, there are these new things which are going on. You be careful because, there are various spoof messages which are coming. You should see in the internet saying that your parcel sent so and so has been held up. You have to pay so much amount to get it released. They just randomly pick up a thing, and there have been people who have lost huge amount of money in this scam. So be careful on that. Okay. So this one was 3 minus N by 1 minus this one. Okay. Where was it here? Sorry. Okay, so R is proportional to M. This is where the goof up is. I understand now. So it is 2 minus 2N, right?
Yes.
Come here. Yeah. So this is the problem. Okay. I was wondering some 5 should have come. It was not coming. Okay. So this will be 3 minus N plus 2 plus, I hope this is okay now.
Minus 2.
Minus 2N divided by 3 minus N which is equal to m to the power 5 minus 3n by 3 minus n. Yeah. Okay. And now this quantity, this thing, delta mr square by mr square will be proportional to, okay, will be equal to, or rather will be proportional to minus, there's a minus sign already here, 5 minus 3n by 3 minus n into delta m will be proportional to this. I suppose so. I think it will be delta m by m. Isn't it?
Yes, yes.
Yeah. There's a mistake in the book which I'm following. Okay. And so this is what proportional to delta omega by omega. So
Since the negative sign.
negative sign is because of this one here. There already is a negative sign.
Okay.
Minus delta omega r square by m r square.
Ah,
Okay. And so delta omega by omega is proportional to minus 5 minus 3n by 3 minus n delta m by m. Now, if mass is added, then delta m by m is greater than 0, implies if 5 minus 3n by 3 minus n is less than 0, then delta omega is greater than 0. Right? If 5 minus 3n by 3 minus n is less than 0, then the other one is greater than 0. So delta omega is greater than 0. Is that
Yes.
okay?
Yeah.
Okay. Now, this of course implies that this thing implies that, so let us see the number line. So this is 0. I have 3, so n equal to 3 is here. And n equal to 5 by 3 is here. Some 5 by 3 may not be here, slightly disproportionate. Pi by 3. Now, if it is, okay, so this will be, so if n is less than 3, but greater than this one, in this region, 5 minus 3n by 3 minus n is less than 0. Am I right? Okay, so this will be equal to 5 by 3 minus n 3 minus of n minus 3. Sorry, let me put it this way. This will be, yeah, it will be 3n minus 5 by n minus 3. So it will be n minus 5 by 3 divided by n minus 3 into 3. So if this to be negative, then the upper one has to be negative and the lower one has to be positive, or the other way around. Okay, so if n is greater than 5 by 3 and n is less than 3, then it is this region where it is negative. Are you okay with me with this?
Yes, yes.
Okay, so this is negative. And in this region, Where n is greater than both, it's positive. In this region, where n is less than 5 by 3, this is negative. Less than, this is negative, this is positive. So it means that if I take this number line, okay, this is n value. Then in this region, 5 minus 3n by 3 minus n is what? Is negative.
Yes.
And implying thereby that delta omega is positive. Whereas in this region, delta omega is negative. In this region, delta omega is negative. What it means is, depending on the value of n, when you have extra amount of mass which is landing upon the spinning system, it depends on n whether it spins it faster or it spins it slower. Do you get this?
Yes, yes.
Yes.
And why it is happening? Let us see. See, for angular momentum to be conserved, if my moment of inertia decreases, spin will increase. And if moment of inertia increases, spin will decrease, right? I into omega.
Yes.
Okay. Now, as I was telling you, depending on the value of n, if I add some mass, depending on the value of n, either the system will contract because of more gravity or will expand.
Yes.
So it means that so by expanding or contracting, it is a rearrangement of mass within that radius. So that is why the small n value will affect what happens to moment of inertia. And depending on whether the total moment because of the interplay between mass and radius, depending on whether the moment of inertia increases or decreases, it will decide whether the spin's rate will decrease or increase. And that is what is happening here. Is this clear?
Yes. Yeah.
You know, this, I don't know whether you appreciate, it's very beautiful actually. In the sense that you just pour something, you don't even know whether it's going to spin faster or slower. It depends on some equation of state somewhere. Okay?
Yeah.
Is the time? It's 12. Okay. Should I continue or probably I'll just continue or I'll just ditch it because I will. Do you want me to take an extra class in between so that it speeds up?
Yes, yes, no problem.
Yeah.
Maybe not, of course, if it is in the weekday, then it can't be. But let me tell you, maybe in the evening, sometime 1 or 2 extra classes I will take. Okay.
Yes, yes.
Okay. So I will share the recording summary as well as problem set for last time as well as this time. Okay. Yeah. Any other thing you want to ask?
Nope.
Okay.
Yes,
Shall I
yes.
have nice weekend or whatever is left of it?
Bye.
Goodbye. Thank you, sis.
Bye.
Thank you,
Bye.
Sish.
Bye.
Thank you, sis. Bye.